The last thing we'll talk about is the second derivative test. So actually, you may remember the first derivative test. I don't know if you remember the name explicitly, but that's where you use the sign chart of the first derivative to determine relative extrema. So the second derivative test will determine relative extrema, but it will use the first derivative and the second derivative, but usually what we use it for is when we don't know enough about the first derivative to make a sign chart. So for example, if we have a table of values or if we have an implicitly defined function. You can use it with polynomials, it's just often used for these other cases. So what it says is let f be a function such that f prime of c equals 0. So that means it has a horizontal tangent slash a critical point. But specifically, it's a critical point where the slope is 0. So it cannot be undefined. The derivative cannot be undefined. And the second derivative of f exists on an open interval containing c. So at this point, same value c, if the second derivative is positive, then f of c is a relative minimum. So let's translate this. If second derivative is positive, that means my graph is concave up. So if my graph is concave up and I have a horizontal tangent, I have a relative minimum. If my second derivative is negative, then I have a relative maximum at that point. So negative means concave down. If I have a horizontal tangent and my graph is concave down, I have a relative max. There should be a third part here. If f double prime of c is equal to 0, this test is inconclusive. It doesn't actually tell me anything. So I will only know if I have a relative max or min if my first derivative is 0 and then either my second derivative is positive or negative. So number 5, we have a function that we know f of 1 is equal to 2. And at each point on the graph of f, this is the slope, 5xy minus x squared minus y squared minus 5. We want to know, does f have a relative max, relative min, or neither at x equals 1? If we tried to use our old techniques to find relative maxes or mins, that would say, look at the first derivative, that's this equation here, and make a sign chart. We can't actually make a sign chart for an implicitly defined function because it wouldn't be, it would actually be two-dimensional, like a grid, not just a number line. And so what we have to do first is, in order to even have a relative max or relative min, we would have to know that our first derivative is 0. So we're checking to see if this is a critical point. So plug into the first derivative first. 5 times 1 times 2 minus 1 squared minus 2 squared minus 5. That is 0. So you can go on to the next step. If you don't get 0 there, automatically this cannot be a max, a min, or neither. If you got something that was undefined, it could be a max or a min, but you would have to have some more information in order to figure that out. In this case, we wouldn't be able to use the second derivative test. So now we're going to have to find the second derivative. I'm not plugging anything in here, I'm just actually taking the derivative of the first derivative. So for this 5xy, I will have to use product rule. The derivative of 5x is 5 times y plus 5x times the derivative of y is dy dx. And the rest I can just take the derivative using power rule. Minus x squared, that's minus 2x. The derivative of minus y squared is minus 2y dy dx. Minus 5, that derivative is 0. Now I'm going to plug in. So I found my second derivative, and now I'm plugging in. So the same point, 1, 2. So 5 times 2 plus 5 times 1 times dy dx, that might confuse you, but dy dx was 0 at this point. So I'm just going to plug in 0 for that dy dx. Minus 2 times 1 minus 2 times 0. So these parts cancel out. That's times a 0 there. It looks like a 9 is a 0. That's a 0. So we have 10 minus 2. That gives us 8. 8 is greater than 0. So that means our graph is concave up, which would mean we would have a relative minimum. Okay, so we do still have to write our justification here. So we're going to say since the first derivative at 1, 2 is 0, and the second derivative at 1, 2 is greater than 0, then f has a relative min at x equals 1. So notice I used the two parts of the second derivative test. So I said f prime of c equals 0, and then the f double prime of c is greater than 0. I have to include both of those. I don't have to say by the second derivative test as long as I've said those two things. For our last problem, we're given a table of values for x, f, f prime, and f double prime. Another important fact is that f prime has only 2 zeros on this interval, and f double prime has only 2 zeros on this interval from -3 to 10. What that means is we can't have sign changes other than at those zeros. And that's important for us to note that it couldn't switch from positive to negative anywhere in between there. If it didn't give us that information, then we wouldn't know for sure, and that would make it hard for us to use the first derivative test. So in part A, it says identify all x values where f has a relative minimum and justify using the first derivative test. So we're thinking about the stuff you must know cold chart, relative min. That tells us we're looking to see where f prime changes from negative to positive. So let's first look at the column or the row for f prime and see where it's 0 or undefined. Those are our critical points. Those are the places where we might have a relative minimum. And then I'm looking to see where it changes from negative to positive. So to the left of -1, I have 1, and then -1, so that's changing positive to negative, so that's not a relative minimum. At 3, I have f prime is 0, and it changes from -1 to 2, so that will be a relative min. This other undefined point, since f is defined, it would be okay for me to call this a max or a min if the sign changed, but notice it was 2 on the left, 3 on the right. And just once again, because I know that those are the only 2 zeros, I know that I'm not crossing the x-axis somewhere in between here, so I know it's not negative. Otherwise, this could have gone down like 2 and then -1 up to 3, something like that. So we will have to write our justification there for x equals 3. F has a relative min at x equals 3 since f prime changes from negative to positive. Make sure you're using the words and not the symbols. The symbols are okay for us when we're taking notes or jotting things down, but use those words in your justification. Part B, it asks us to identify all the x values where f has a relative maximum, justify using the second derivative test. Now, if this didn't tell us to use second derivative test, or it told us to use first derivative test, we could say that there was a max at x equals -1 because the derivative changed from positive to negative. However, we are using the second derivative test, so we're going to have to use a different justification. So we're looking to see where f prime is equal to 0, and because this is asking for a relative maximum, I want f double prime to be negative or less than 0. So double check here at that same point we looked at before. I see that f prime is 0, and I see that my f double prime is negative. At my other zeros, I see that this is positive, which would confirm what we said in A, that this is a relative min. We cannot use second derivative test where our first derivative is undefined. So those are the only 2 possible points we'd be looking at. So again, we'll write our justification. F has a relative max at x equals -1. Now we're using this idea here for this to justify the second derivative test. Since f prime of -1 is equal to 0 and f double prime of -1 is less than 0. You don't have to say is equal to -1. It's really just that it's negative there. Last part, part C. Find the equation of the tangent line to f at x equals 5 and use it to approximate f of 5.1, and then decide is this an over approximation or an under approximation and justify. So we're using that same idea that we did at the beginning of the notes. So our point, so this has at x equals 5, so f of 5 is 3. My slope, f prime of 5 is 2. And so my tangent line equation, y minus 3 equals 2 times x minus 5. Now let's find our approximation. We're approximating f of 5.1. So f of 5.1 is approximately 2 times 5.1 minus 5 plus 3. Again, you do not need to simplify that. The last bit is this an overestimate or an underestimate? So remember, we're going to look at the second derivative for that. And specifically, we're looking for the second derivative between 5 and 5.1. We can look at a bigger interval if we want to as well. Let me erase these other highlights that we did so we can focus on the parts that we want. So I'm looking between 5 and 5.1, so on this interval here, and actually if I look at f double prime, I know because these are the only two zeros, it will be positive everywhere between 1 and 7. So that's the interval that I want to zoom in on. Otherwise, I would not know for sure if it changed signs in between there. So we can say since f double prime of x is greater than 0 for x between 1 and 7, then this is an under approximation for f of 5.1. So remember again, if our second derivative is positive, we're concave up, which means we're an under approximation for that tangent line.